All right, good afternoon. We're going to start the third talk in the case studies track, Kubernetes, the new research platform, given by Lindsey and Bob. Pretty interesting, especially when you think about what research institutions have to go through, especially about offering up compute so that researchers can actually do the work that they need. So be sure to go into the app and rate this session afterwards. Also, we'll take questions at the end as well, and I'll run around with a microphone at the end so that everyone can hear. And also, it is being recorded, so we want to make sure that the questions get on the recording as well. So, Lindsey and Bob.
Okay. Hi, everyone. Thank you for coming to our talk. This is Kubernetes, the new research platform, and I am... One second.
There we go.
So what do I need to do?
You're good.
Okay. And I am Lindsey Tulloch. So I am just finishing up my undergraduate degree in computer science at Brock University.
Hi, my name is Bob Killen. I am a senior research cloud administrator for the University of Michigan. I am also a Cloud Native Computing Foundation ambassador with a focus in academic outreach. And this is Kubernetes, the new research platform, or as I really like to think about it, a tale of two research institutions. So there will be a little bit of back and forth in this presentation, this case study, because it's sort of how we gained traction or adoption of Kubernetes at both our institutions. We both sort of came to the same conclusions, encountered some of the same problems. That sort of dig into like why. So at both of our institutions, we've seen an increased usage of containers, well, everywhere. And I think that's pretty safe to say in the general research community as well. And this isn't just like what we normally think of as containers, but also through other sort of like runtimes like Singularity, Charlie Cloud, and although those are more meant for like HPC systems, they're still containers and still sort of relevant to us. But one thing we've really seen is a general movement away from sort of the strict style job workflow and a greater need to sort of support things like data streaming services with in-flight processing or eventing. So a lot of things like Kafka, Spark, Flink, and a just general dependence on more sort of like persistent services, things like databases, other things sort of like interactive science gateways like Jupyter Hub. And these are things that don't classically mesh well with HPC. Now, this sort of brings us to why Kubernetes? Well, both our groups, again, sort of came to the same conclusion in that Kubernetes has become the sort of standard for container orchestration. Like it or not, it really is. And the big thing is, what it can't do, it can be extended to do. And if it can't, and it can all be done while essentially avoiding vendor lock-in. So what I do is reproducible by someone else that can get a Kubernetes institution up, or Kubernetes installation up and going. And so it's been a big boon for reproducibility in science. You don't have to change anything. If you have a conformant Kubernetes cluster, if I can run this here, it should be able to run there. There's been a lot of other just general traction in the Kubernetes ecosystem. There's about 8,000 attendees here. We got 66,000 people in the Kubernetes Slack, and well, just a massive amount of adoption. But with that little bit out of the way, I actually want to hand it back over to Lindsey to sort of go over things from a research perspective, and I'll cover things a little bit later as more of a service provider perspective.
So this little right arrow key.
Yep.
Okay, perfect. Okay, so as I mentioned, I am just finishing up my Bachelor of Science in Computer Science at Brock University. And Brock offers an opportunity to do a work placement as part of your degree. So I actually spent 16 months as an intern at Red Hat working on multi-cluster Kubernetes, and that was kind of my introduction into the Kubernetes community. And when I was returning back to school in September, I had a few more credits to finish up. So I was thinking, how can I finish up my degree and still continue learning about Kubernetes? And so I decided to approach my previous research supervisor that I had done a research project under before and ask for her advice about how I could incorporate Kubernetes into a research project. And my previous research was under Dr. Sheridan Houghton. Her specialty is in bioinformatics, and the research that I did previously was on an algorithm called the Salmon algorithm, which was developed by a previous master's student. And the Salmon algorithm is a metaheuristic algorithm that takes concepts from genetic algorithms and ant colony optimization to solve combinatorial optimization problems. In other words, it's an algorithm that has a bunch of tunable parameters and a memory of best path that is passed through a bunch of iterations with the aim of solving computationally hard problems in a really hacky but expedient way. And it can be configured to give significant results for the DNA fragment assembly problem, and this is essentially what makes it a bioinformatics algorithm, just to demystify the term a little bit. So when I brought up the idea of using Kubernetes in some way, my supervisor suggested that as a first step, I could try running the Salmon algorithm on Kubernetes. It's going to show up. But there was a small catch, and that was to try and get it up and running on Compute Canada. At the time, I had not heard of Compute Canada. I suspect many of you also don't know about Compute Canada. So let's learn about Compute Canada together. All right, so Compute Canada operates at a national level through partnerships with regional organizations. So there's AceNet on the east coast of Canada, Atlantic Canada, Calcul Quebec, which operates in Quebec, Compute Calcul Ontario in Ontario, and WestGrid, which covers the West Coast. Each organization supports local researchers with advanced research computing systems, storage, and software solutions. And for those of you who are not as familiar with the map of Canada, this is what it looks like. So WestGrid covers the West provinces, Compute Ontario in Ontario, Calcul Quebec in Quebec, and AceNet in Atlantic Canada. Yeah, and they serve over 70 institutions across Canada. Okay, so Compute Canada is appealing to many Canadian researchers because all Canadian faculty members have access to Compute Canada systems and are able to sponsor their students and postdocs for no fee. So this provides greater compute power, expertise, and resources than are typically available, especially at smaller research institutions that have limited funding and resources. And this data is from 2016, but it kind of gives an overview of the different types of research that Compute Canada is being used for. As far as resources go, Compute Canada has compute and storage resources spanning across 5 to 10 data centers with 300,000 cores, 12 petaflops, and 50 plus petabytes of storage. There's a team of about 200 experts with at least one place locally at each institution across Canada. And these experts help out with the installation and configuration of hundreds of research software packages. So the mission of Compute Canada is to put as few restrictions as possible on types of workloads that researchers can run, and with the idea that researchers drive innovation. Most production work currently is done as batch jobs on compute nodes via the Slurm scheduler. And as Bob alluded to earlier, Compute Canada's user base is broadening, and it's bringing in a broader set of needs. So there's currently a tremendous interest in services enabling research data management and other things that Kubernetes is really good at solving. All right, so back to the Salmon algorithm. So now we know a bit about Compute Canada, but it's still not totally clear how I'm going to get the Salmon algorithm running on Kubernetes on their resources. As far as I can tell through my contact with the Compute Canada expert at Brock, there's no Kubernetes cluster that is currently up and running on Compute Canada resources, and no restrictions on researchers doesn't mean they're just going to hand over admin privileges so that I can deploy it myself. So this is a challenge that will have to be overcome. The other issue is that there are 200 experts, but this doesn't mean that there are 200 Kubernetes experts. So even if I am able to deploy Kubernetes, There's not even one Kubernetes expert, just to be clear. Well, so even if I do get Kubernetes up and running, or even if I do get admin access to some sort of resource, I'm not going to have any support doing it. So this is starting to look a little bit more complicated than I originally thought. Fortunately for me, there were other people that were also asking similar questions about running Kubernetes on Compute Canada resources. And it turns out that those people were CERN. So there's an Atlas collaboration at the University of Victoria. It was founded in 1992 with the University of Victoria being one of the founding institutions of the Atlas collaboration. And Atlas, as some of you may know, and you may learn about later tonight in the CERN keynote, Atlas is located on the Large Hadron Collider ring and detects and records the products of proton collisions in the Large Hadron Collider. It was built by researchers from 150 universities and 35 countries. The LHC and Atlas together form the most powerful microscope ever built, which allows scientists to explore space and time and the fundamental laws of nature. So, like, no big deal or anything. Where did the speaker notes go? Sorry, 1 second. Oh, there we go. Okay, so Atlas produces several petabytes of data per year, and they require a lot of compute power to process this data and also filter it before it's actually made into tangible results. So there's a tier 1 compute center that's based in Vancouver, and then the tier 2 computing center is at the University of Victoria, and this is where final analyses on the data from Atlas are performed. So the UVic Atlas group consists of 25 scientists, students, professors, technicians, and computer experts. So where exactly does Kubernetes fit into all of this? So work currently at the University of Victoria builds off of previous work where a method was developed to deploy a Kubernetes cluster as an Atlas computing site. And some of the details you can see from the image. The Panda workload management system used by Atlas is able to consume Kubernetes if a Kubernetes endpoint is provided for it. And then it's able to spin up Atlas jobs by provisioning the resources on the computing sites they have access to. CERN is kind of the poster child for high throughput computing. There's no need to coordinate since the jobs are embarrassingly parallel. And this is a great example of Kubernetes use that provides incentive for Compute Canada to get on board. So this is all looking good for my research. Danica McDonnell is a PhD student at the University of Victoria who generously shared this information with me to present at KubeCon. And the work she is doing is testing the usability and performance of the setup that I mentioned as a production level computing site. So she's testing things like reliability, resource utilization, and scalability. So once I was able to get in touch with the Compute Canada researchers involved on the West Coast, things got a lot easier because they were a lot more interested in what I was trying to do. So I was able to get an Arbutus Cloud project, access to an Arbutus Cloud project, which was an OpenStack instance with the maximum resource allocation. And this is some details about what all that included. It was a lot more than I needed in some cases, but anyway, it helped. And then one of the people that was involved with the CERN project ended up deploying Kubernetes with Kubespray, Terraform, and Ansible. So I was able to use that work to deploy Kubernetes. Of course, this is not the only way to deploy Kubernetes on OpenStack, but it's one of the ways, and that was the way that I used. And then from that point, it was relatively simple to containerize the Salmon algorithm and create an Argo workflow to run the research job. And actually, if it hadn't taken so long to get the Kubernetes deployment up and running and figuring out all the other stuff with Compute Canada, it would have been really great to spend more time investigating like the Argo, what all can be done with Argo, Kubeflow, and other projects that Kubernetes allows you to use. But just to talk about my Argo workflow, to be statistically relevant for a scientific paper, you need to run an algorithm 30 times and then aggregate the results. So for a proof of concept, my workflow generates 30 random seeds and then feeds them into 30 instances of the Salmon algorithm running in 30 different containers, sends the output to a persistent volume. I wrote a Python script that aggregates the data and then finally prints out the result. So this is a sample result. Hopefully you can read it, but it shows the 30 different jobs and the average best path. Amazing. Okay. So since I'm just a researcher, I can't really say what the future of Kubernetes on Compute Canada resources will be. But if it's in line with the stated mission, researchers like CERN are driving innovation, and this is true with Kubernetes as well. But the learning curve is very steep, and researcher time is precious. So as I said, I spent a lot of the time that I was working on this project trying to just figure out how to get Kubernetes deployed, rather than exploring all of the tools that I could use if I had a Kubernetes cluster. So if it was just a matter of learning YAML and Bash and all those things, it might be reasonable for a researcher to learn. But having to deploy Kubernetes and learn everything from that level is probably not the best use of time. But yeah, I'm going to pass it over to Bob and let him talk about it from a provider's perspective.
Okay. So it's sort of our job as providers to, well, prevent that from happening and offer something up that a researcher can consume. And sort of to tell you a little bit about that and how we enable that, I first need to tell you a little about the University of Michigan as a whole. So we happen to be one of the largest universities in the United States with 19 schools and colleges catering to about 45,000 students and roughly 8,000 faculty. We have 100 graduate programs in the top 10 according to US News and World Report. And sort of the more relevant statistic of this conversation is we happen to be #1 in research volume among all US public universities according to the United States National Science Foundation. And sort of backing that up is we have just under about $1.5 billion in annual research expenditures. So while we aren't anywhere near the size of Compute Canada, we're a pretty good size institution and we're also pretty decently far along with Kubernetes. And to tell you a little bit more, I need to actually dive into a little bit the department that I work for. So I work for ArcTS, or Advanced Research Computing and Technology Services. And because the University of Michigan has such a large sort of research footprint, it sort of warrants its own department to handle the research needs and sort of streamline the researcher experience. So we are essentially tasked with handling the computational research needs for the entire university. We want the researchers to come to us and consume the sort of services that we provide instead of buying a computer and putting it under their desk. So essentially we're a RPaaS, or sort of research platform as a service. I hate that, but it's kind of true. So we're a little bit of infrastructure as a service, a little bit of software as a service, a little bit of container as a service now. Sort of backing all that stuff, our group is roughly 25 people, and sort of our bread and butter is still our classic HPC, and we have 27,000 cores. We also have a restricted data side, restricted data cluster that has about 14,000 cores. We also have various other platforms, both ARM and Power, whack loads of GPUs. We have various data science initiatives, so a fairly large like Hadoop cluster and Spark. We also have on-prem virtualization services, and because research grants are now coming with cloud credits, we have a presence or have had to deal with every cloud provider. And honestly, the burden of trying to manage all of that is kind of insane. So supporting all these different systems is its own set of challenges. And everything that was on-prem that I mentioned generally can't get out to the internet for security reasons. I.e. we don't want like a compromised account consuming researchers' allocation to like mine cryptocurrency or something like that. Not to mention there's other various research that's under like export controls. So many of the services that we would normally consume have to be mirrored internally. And instead of standing up a bunch of virtual machines or installing on bare metal, we went the Kubernetes route. So we got general buy-in for this initially just by a bit of dogfooding. We needed a moderately highly available platform. If our system goes down for a few seconds, it's no big deal, but the system should be able to quickly recover. So we started by hosting our sort of ancillary systems, so things like patch mirrors, build systems, source repositories, logging and monitoring, along with other things like identity management services. And sort of once we cut our teeth and got sort of all the kinks worked out, we decided to open it up. And we created a sort of container as a service offering called ODS, or on-demand services, that was more meant for our researchers. And when we gave it to them, we learned a lot of things. Well, they needed a sandbox to do literally anything and everything, and that was kind of crazy. When they needed to do it with being able to stomp on each other. So initially, we had many requests for various database systems, and that was mostly to augment jobs that were running on our HPC cluster. And then we had other things like CVMFS, and Squid, and then it sort of grew to sort of custom application stacks like Clouder, a large data management suite used by our digital humanities group on campus. And honestly, digital humanities is an often underfunded area of science, and being able to provide them a fairly resilient platform was a huge boon to them. We also had another group and sort of built their full-blown app stack. That sort of combined a mobile app and hosted app along with machine learning and a bunch of other stuff along the way that studied hybrid transportation model. So think sort of a combination of Uber or Lyft with public transportation. And there certainly are others, but if you look at this, there's one big thing that's missing. I'm sure some of you can guess it. Jupyter Hub. For classes, science gateways, and as a general means to integrate with our other services, this has been our #1 request by anyone and everyone. Our Jupyter Hub instances are 100% controlled through Git. So a new instance for new class or new research project is one commit away from having its own DNS name, cert, and if needed, its own namespace to function. And something has sort of grown from this. As our researchers have sort of grown to consume this, they've started to explore more of the ecosystem and are starting to realize sort of other aspects of the research process, and they can be made easier. And this has led them to a little thing called Kubeflow. So why Kubeflow? Well, Kubeflow bundles up a slew of different components that makes them easy to deploy and very consumable from an end user research perspective. Now, we don't actually have any GPUs in our current Kubernetes offering, Kubernetes cluster, but that doesn't mean those tools aren't useful. A good example here is the MPI operator. So that can be used with other things like Uber's Horvath model for training as a training alternative to a distributed TensorFlow job. And there's also a whole slew of other possibilities that sort of fall into the MPI space. Not to mention there's other things that are more broadly usable that can be run anywhere, like Argo. The big thing is this has actually gotten researchers and honestly other support staff and more people thinking more about sort of the new research lifecycle or research software engineering more. And while this graphic is sort of centered around machine learning, it can be applied to much more than that. And there's a lot more. In today's data science and machine learning workflows, there is so much more involved sort of in the general research process. Researchers are iterating more on the data and need the tooling and hosting to be able to do that well, and preferably in a very reproducible way, so that way someone can just pick up what they've done, take it, and run it someplace else. And so this has acted as a little bit of a forcing function. And we saw this initially sort of with OpenStack, as the flexibility opened up sort of a lot of doors, but it also left a lot to be desired. You still had to sort of manage VMs and then manage the application stacks on top of it. And Kubernetes as a platform solves many of those pain points. Now, that's not to say it's necessarily easygoing. There are certainly some challenges. So first and foremost, Many institutions, us included, have invested sort of heavily in, I would say, the classic multi-user POSIX infrastructure. So this is things like distributed shared storage, so things like Lustre, GPFS, and things like, it's kind of hard to take a API identity or like OAuth 2 identity and translate that to like a UID and GID that can propagate down to the file system well. There's some workarounds that we've done. Both myself and my coworker Jeff, who's over there, have written some things to help take care of that. But I wouldn't call it like prod ready in any way, shape, or form. Well, I'll say publicly consumable in any way, shape, or form. Another thing is like the installation experience with bare metal is still kind of a pain point, but there's several efforts underway, specifically like around the cluster API that might help improve that. The other thing is that for a lot of our researchers, like Slurm and Torque are like, they're used to using those, and they're honestly at a bit more of an advantage when it comes to scheduling, because again, like a classic HPC job sort of like falls into a queue and has a wall time, so you explicitly know, when the job will start and end and where you can fit it, or like whole node scheduling is much more common in the HPC community. That's very different from how we do things in Kubernetes. Now, despite all those challenges, our adoption rates have been good. So I'd say this is about where we are today amongst our users. General users, they just want like a consumable endpoint. Like they put in a request for a Jupyter Hub. We say we'll provision them Jupyter Hub, and they're happy to go to a URL. We also have a set of like intermediate users that don't necessarily want access to Kubernetes, but they're just happy being able to manage it all through Git. So they want to be able to push their own image, make a few changes to a deployment. They don't need direct access to the cluster. They just need to be able to, again, manage it through Git, and if a mistake happens, they can revert. And then we also have a set of advanced users, sort of like that group I was describing earlier, as building like a whole app stack that actually just want to sort of consume Kubernetes itself. And we're able to give them that access by essentially giving their group a namespace and locking it down with RBAC and PSPs. So like, for example, users can't run as root. They can't run privileged, and they must supply like resource limits on all their, like requests. And we expect this distribution to change with some of the things we're working on in the future. So first and foremost, we plan to move to bare metal. One of the big things has been, hey, I have these 27,000 cores over here with no virtualization layer in between. Why should I run over here? And we're hoping that that might placate some of those concerns. The other thing is that we are potentially looking at other platforms or other architectures. So possibly Kubernetes on both our ARM and Power infrastructure. We are, as I sort of hinted at earlier, working on like actively improving the whole like UID GID mapping problem, so that way they can like integrate with our home directories, as well as automating some of the like Kerberos and knitting from containers to more easily integrate with our other services. We're also keeping a very close eye on some of the hybrid work being done. So Scilabs has a Slurm operator that sort of lets us integrate with our sort of larger HPC cluster, where I can create like a Slurm job in Kubernetes, and I can interact with that in a normal like Kubernetes way, as well as any other tooling, and that can then go off to sort of our HPC cluster, do its thing, and then the information can bubble back up into Kubernetes. The other thing is that we use like the LSF scheduler for our power system, and IBM has been working on a sort of drop-in replacement for the Kubernetes scheduler that uses LSF instead. Now, let's see. There's also sort of like interest now in sort of I would say the Kubernetes native way of doing this. And this is Kubernetes native way of sort of doing like gang or co-scheduling. And this is mostly for things like MPI jobs. A couple of the projects, there's like kube-batch, which is sort of adding that co-scheduling functionality, and this is sort of centered around what's known as pod groups. And then there's also a new project called Volcano, which is adding like queues, a CRD for MPI jobs, index jobs, and also has some like other sort of advanced scheduling options like fair share. And I'm honestly not as familiar with it as I'd like to be. It's a pretty new project, but I definitely will be exploring it more. And there's also one area that I'm going to be diving into big time. And that's outreach and training for both our faculty and students. We know Kubernetes has a high learning curve, and it can put a lot of people off initially. And we've sort of started this project already. We've been running classes internally on how to build containers well. That's also a big problem because in the research world, you find containers 15 gigs in size. And once they sort of go beyond that, we then sort of teach them sort of how to use Kubernetes. And as we sort of go through the process of teaching them, they sort of have this little aha moment and sort of start to realize the power and flexibility that it offers. And so with these sort of efforts that we're doing, we're sort of expecting our changes to go from this, the chart from earlier, to this. And we hope to see this within the next year. So as we improve our offering and focus more on the outreach, we expect to see a general shift to more intermediate users and more advanced users. And as service providers, we want to build, offer, and run a platform that enables our researchers to more effectively share, collaborate, and honestly do their research. And Kubernetes is a platform that lets us do that. And while there are definitely some rough edges, we expect those to improve, especially with greater adoption. And with that, I will hand it off to Lindsey to bring it home.
Okay, we did want to leave a couple minutes for questions, but I'm just going to do a quick conclusion. So to recap the major points, we have seen that Kubernetes provides a lot of great things for researchers as well as research providers. There are lots of existing tools that facilitate research workflows such as Argo, Kubeflow, and kube-batch, and there's a growing demand from researchers for a tool that does everything Kubernetes can do. So we do have a quick couple of suggestions for increasing Kubernetes adoption. Most of the provider ones Bob has already talked about. So one is offer Kubernetes for people to consume. This is kind of a if you build it, they will come situation. Get involved with the Kubernetes community. There's a lot of really helpful, knowledgeable people, and a lot of them will be more than willing to answer any questions that you have. If you join a SIG call and tell them your use cases, that is often very helpful and informative for developers. Learn as much as you can. Again, this goes in part with the previous one. And as Bob mentioned, provide outreach to researchers and anyone that might need help being ramped up. And for researchers, engage with the research institutions. If you're interested in running Kubernetes, let your research institution know and tell them about all of the great things that it can do if they're not aware already. Get involved with the Kubernetes community. This was the same suggestion for providers. Learn as much as you can. This might also sound familiar. And share your findings widely. Write a blog post, make a YouTube video, do a proposal to speak at KubeCon. Whatever helps to get the information out there to other researchers. And that's it for us. So there's some useful links that you might be interested in.
It's all in the, if you download the presentation, it's all in there.
And thanks to Atlas, CERN for the images, the VISPA website, which is the University of Victoria website, and Compute Canada for the usage information. And with that, we'll take any questions if there are any for 2 minutes.
Okay, hello everyone. I want just to ask what kind of underlying network you're using, or software-defined network you're using for this installation.
Ian, sorry.
The underlying network that I was using for, I'm not sure. I'm actually not sure. Oh, okay, I'm using Calico. I did not know that. You don't need to know everything, everyone.
We're using Cilium.
How does your Kubernetes 101 class look like? Like the introduction to Kubernetes.
The password?
you provide training for Kubernetes, right?
Sorry, I can't really hear.
Yeah. The question is, you mentioned that you're educating people in your institution of how to use Kubernetes. What does the training course look like for that Kubernetes 101?
So if you go to github.com/MrBobbyTables/K8's intro -tutorial, it's pretty much that. It's also in the if you go to the CNCF presentations repo, it's linked under there as training. We also have our container training up there, and then a lot of the other stuff is a bit more one-on-one or with smaller groups. That's more focused on improving their containers. So they'll come to us with a very large container, and we'll walk them through you don't need to have these 24 run steps. You can just essentially use one or two, or use a build container and flatten them and things like that.
We can probably do one more if there is one.
Yeah. I can also be found over there too after this. Well, we can be found over there for questions. Sorry.
Maybe a question for Bob. How many clusters do you run, and how big are they roundabout?
Okay, so we have 3 clusters. We have one that is our general services cluster, and this sort of provides services to our other clusters, so our identity management and things like that. We have one cluster that is sort of the public-facing cluster that we give most of our general researchers access to. And then we have a 3rd cluster that is for restricted data services, and that's very tightly locked down. Our general cluster isn't too big. It's collectively, I think, 512 gigs of RAM and 15, 20 nodes? 10 nodes. Okay, yeah. So not terribly large, but we have a pretty good amount of users using them sporadically.
We'll do one more. I said last one, but we'll do one more.
Hello. Because the containers are not meant to be, persistent or reliable, how you deal with data integrity passing through the containers?
Our data integrity hasn't been a big issue. We use we either do binding to a single host for things that don't work well over NFS. Otherwise, we use NFS as our sort of storage provider used by our other services.
Let's give Bob and Lindsey another round of applause.